Schedule, there is this talk called audio networks and the security implications, and you're probably going to, well, why do we have security implications with audio networks? It's all XLR and analog, and there are the security issues, right? Well, apparently the world moved on, and now it's all audio over IP, and especially with commodity hardware. So here to talk about audio networks and security implications, please welcome with a very warm round of applause, PCWiz.
Hi. Hi. Yes, I'm PCWiz. I work for the company that put the sound system in Abacus, if you've heard that. You probably definitely heard that on Friday night if you were here. But this is my own work outside of work. So I've been sort of doing my own research. But I work in that field, and that's why I'm sort of looking at it. So I'm hopefully going to introduce you to audio networks, what they are, and where they're deployed, and get you a bit interested, and also show you just how soft they are as a target. And then after showing you how soft they are as a target, hopefully people are interested enough to think about it, and maybe when people think about it, we can change it. So where are audio networks deployed? Well, Abacus, but also big broadcast situations. So think about Olympic Games. You've got lots of stadiums, lots of broadcasters, lots of different people. You've got to provide public address inside the stadium for the people watching in the stands, and you've got to provide media streams that all of the various television and radio broadcasters can use to create their coverage. And what tends to happen when you make an audio network is that they extend to places you don't expect them to go to, especially in places like theaters, for example. It's increasingly common now that your bathroom also has an audio feed from the stage, so you don't miss anything when you go to the toilet, which is really convenient, but now means that you've got audio access inside your bathroom. So that might be a problem, thinking about the things we're going to talk about later. And yeah, anybody who's got any experience doing penetration tests will know that bathrooms are quite a good place to have plenty of private time with network equipment. Okay. So why are we deploying these networks? Because, well, no one deploys technology just for the sake of it, unless you're at a hacker camp, in which case maybe you do. It's mostly, well, cost. Everything in AV is moving in this direction for IP-based networking. So you've got ArtNet on the lighting side. You've got various different video networking standards, and obviously ancillary stuff. So your show control. Everything is going over IP networks nowadays. So you can save a lot of money by building one IP-based infrastructure and dragging one set of cables inside your building, and that's pretty nifty. Yeah, and if you're thinking about, I shouldn't touch the microphone. It's also more versatile because you can share your audio feeds a lot easier with multiple places. So sharing in the Olympics again between the public address system in the stadium and the multiple broadcasters outside is really easy. You just sort of let them attach to the network, and then they can ask for those audio feeds, and it doesn't have to go through any special box. The network takes care of transporting the audio there. So it solves a lot of problems. It's really nice. And it's also really helps with consistency. I don't need a box of lighting cables, a box of audio cables, and a box of whatever else. I just buy some single mode fiber and some Cat6 cables and some normal, or fairly normal switches, and everything's good. If something breaks, I can just go to the local IT supplier and probably buy a replacement. It's nothing which is special to the AV industry anymore, really, which really improves your business continuity, especially if you're touring and you need replacements for things. Okay, so why am I going to talk about the network and not the hundreds or maybe thousands of insecure Linux devices that are sat on the network? Probably because it's more interesting to me, and because a lot of people will already talk about hacking embedded Linux devices, and I could do a separate talk on that, but changing the network is going to be a longer-term goal, because that requires integration between multiple different players in the industry, hardware vendors, software vendors, and of course adoption by people, and that takes a decade at least, even once you've got a standard in place to get that built into hardware, built into software updates, and then actually deployed. There's a lot of work to be done, so I thought I would highlight the topic now, and hopefully we can start to agitate some change. So now I'm going to get into a section where I'm going to run through some attacks, and we're going to sort of build up the knowledge we need to understand the system one attack at a time. So I've got 3 different attacks, and what kind of attack objectives might we have? So we can damage people. Obvious way to damage people is play something really, really loud and create hearing loss. Less obvious way is just disrupt the system during some kind of emergency announcement, and you can create quite a lot of panic, and then you're really going to have problems with panicking people. You get crushed people, and that's not great. If you saw on the previous slides, we also deploy audio networks in transport hubs, like train stations and airports. So definitely places where you want your public address to work. You can also damage equipment. You can play square waves out of the speakers, and the transducers will pretty quickly burn out if you play a sufficient amplitude. So yeah, and then there's also reputational harm, which could go together with snooping. You've got a big star, and then you get a recording of their microphone while they're off stage doing something less than ideal or saying something less than ideal, and well, you've just got some blackmail material or created a very sticky situation. And of course, disinformation. If you can control the audio coming out in especially a broadcast situation, then it's like in the movies. I mean, you can do whatever you like. You would hope you couldn't, but there's some soft bits on either side where you probably could if you've got time and effort, time and motivation. So let's start off with snooping. Right, we've got an analog audio system here. We've got a microphone, a stage box, and a mixing console. Pretty simple. There's an XLR cable that goes into the stage box, and then there's an XLR snake or maybe Ethernet cable doing like AES-50, which is not IP-based, but a special thing that also happens to use Ethernet cables into the mixing desk. And it's pretty hard to intercept that. It's going to be detected very, very easily. Because if I unplug the cable, the audio stops. The guy sitting at the front of house is going to notice the audio stopped. It's hard to attack that situation. But let's make this a network. Okay, we've got a switch in the middle. Great. Well, now I can plug it and unplug things without the guy noticing necessarily. That's already a start. So how am I going to tap this? And for that, we're going to need to explain unicast and multicast. But here's our attacker, who's clearly motivated to spy on what's coming out of his microphone. So just some quick background, because I also need to explain multicast, because in most network situations, multicast is something you burn with fire, and then pretend doesn't exist. But in media applications, it's quite necessary, unfortunately. So to explain it, this is what unicast looks like. You send the same feed multiple times from your source, which is great. If you have a handful of devices that need to receive this audio, send unicast feeds. It works. You've got, but what happens with unicast is that you start to consume all of your transmission bandwidth on your source, and then you cause congestion. And especially in audio networks, we don't like congestion, because congestion basically increases our latency and increases our jitter and makes our audio networks less stable. And if we're trying to operate in a low latency environment, for example, doing public address on a stage, when we need low latency, somewhere in the sort of under 2 millisecond range would be nice. So we have to send a different stream for each device. And this is also somewhat vulnerable, because you can just ARP spoof, and then as long as you forward the packets quick enough, the person on the desk might not notice, but you have to be very careful about your forwarding, because the latency is quite sensitive. So expensive network cards are advisable if you're going to ARP spoof and intercept unicast in an audio network. But luckily for attackers, well, we use multicast most of the time, so it's actually much simpler. So we solved our problem of the source transmission bandwidth, because the source just sends it into the network, and then it's the network's job, so the switches in the network, to understand who is part of this multicast group and who wants this network traffic, in our case, audio. And the basic way that this works is someone, well, usually the router or a switch, is a querier, and it asks everybody in the network, what multicast groups would you like to be part of? And then everybody in the network replies with a list of the multicast groups that they'd like to be part of. This traverses up the tree of switches, and you basically end up receiving that multicast group. So all you need to do to snoop on the audio is plug into that switch from earlier, say, look, find out which multicast group has the audio you want in it, and join it. And then you can packet capture. And Wireshark has a really handy tool which will take an RTP stream and just turn it into a WAV for you, which is pretty nifty. So that's snooping. It was very easy. Yeah. So what else can we do? Okay, we can disrupt the network. We can disrupt audio coming out. We can create audio artifacts. We can make dodgy noises come out of the speakers. We can just make the system not work, which, depending on your objectives, could be interesting to you. So the thing to attack here is the clock on the network. Clocking is extremely important on media networks, because to get phase alignment for the 48 kilohertz audio stream, so if you've got 48,000 samples of audio per second, and that's your media clock, then you need accuracy for your wall clock within about one microsecond. So it's a very high accuracy clock that you need available in your network. Otherwise, you get phase alignment issues, and then you get various interference patterns, especially in AV setups like this. So if you even adjust the clock minutely, you're going to cause problems for people. So how are clocks distributed? How are clocks distributed on these networks? Well, they use the precise time protocol. It's in the name, really. And what it does is it has a leader, which unfortunately in IEEE terminology is called a grandmaster, but I will not use that term from here on. This basically is the best clock in the network, theoretically. And this should, in theory, also be backed by GNSS, so it should be a satellite-derived clock. And this is going to also help you when you come to stream audio between multiple sites, because the precise time protocol only works within one LAN, so within one network, within one site. You don't want to run the precise time protocol anywhere else. Running the precise time protocol over a WAN will not go very well, because it basically calculates lots of delays and sort of makes some assumptions about how Ethernet works, and it does a lot of clever things and relies on a lot of clever assumptions about how local area networks work, and it doesn't extend so well over the internet. So yeah, that's where that works. Anyway, so precise time protocol, you've got the sort of main leader at the top of your tree, and then you might have boundary clocks or transparent clocks in your network, and those are typically switches. And these boundary clocks will basically act as they will listen to the leading clock on one interface, and then will lead clocks on the other interfaces, which helps take load off your main clock lead. And a transparent clock is really just about providing increased accuracy, which you'll find in newer switches, because it basically measures the time that your packet is inside the switch, and then provides that information too, which is quite useful for understanding the delay and the jitter on your network. Yes, I covered all the notes. Yeah. Yeah, so if you're on a LAN, it's just PTP. If you've got multiple sites, then because they're both based off a satellite-based clock, they should be coordinated and pretty much aligned, so you can have a broadcast coming from South Africa and streaming it somewhere and mixing it in Brazil, and it should work just fine as long as you've got access to satellite time. But of course, we can disrupt this clock, and then things will go wrong. So one option we have for disrupting this clock is by rigging elections, because the lead clock is elected naturally based on its characteristics, but not just its characteristics. It's also elected based on two user-controllable priority fields. If you ever touch a media network, you will probably find out very quickly that you have to configure these in order for it to work correctly. You'll find a lot of media networks where they basically denial of service themselves because they're not properly configured. And the thing that isn't properly configured is the priorities in the PTP announcements for the election of clocks. But in reality, if you're an attacker, you can change all of these fields. And basically what you want to do is say, I have the lowest priority, which the lowest number of priority gives you the highest score in the election. And you can sort of fake your accuracy, and instead of saying you're an internal oscillator, maybe you can say you're an atomic clock or something, if you really, really want to be the clock. So if you want to be the clock, it's pretty easy to be the clock. So you're the Time Lord now. Great. So if you want to make the clock drift, you can make the clock drift. If you want to make the clock jump, you can make the clock jump. You can do whatever you like, and it's pretty much as simple as running PTP for Linux on your laptop, and have fun with that. There's another option, of course, You can do a denial of service, you can generate some traffic, but you don't have to generate that much traffic because audio networks rely on prioritization happening within the switches to achieve different amounts of latency and different traffic classes, basically. So the clock is the most important, and this goes into the expected forwarding class. The audio is the second most important thing, and this goes into assured forwarding, and everything else is best effort. And what this relates to is that a switch typically has a couple of queues, like 8 or so, and there's basically a load balancing algorithm that prioritizes certain queues, like the expected forwarding queue over the assured forwarding queue, and then the assured forwarding queue over the default forwarding queue. And this basically tries to make it under certain conditions that you don't lose your clock packets, and that you don't very often lose your audio packets, and that the jitter applied to them is also lower. So all you actually need to do is send enough traffic labeled with this field with the correct value, and then you fill up the queue where the PTP should be going. And when you filled up that queue, then the PTP will start to deteriorate quite quickly. So you don't need to saturate a lot of the network to cause problems. And if you're just aiming for chaos, then that will give you chaos. Okay, now we move on to possibly the most interesting attack types of this presentation. Actually hijacking audio streams. So how can we get the speakers to play our audio, or how can we get the broadcast station to play our audio? So we've got the first option, which is pretty trivial. All of your audio streams will be announced on the network somehow. This example is from a Ravenna implementation, so it's using the session announcement protocol, but you'll also see Dante using MDNS, but that really doesn't matter, because always inside MDNS or the session announcement protocol, you will find the session description protocol, which is the same in both Dante and Ravenna, basically any audio over IP solution. And what you find in here is basically the multicast group where the audio is being sent to. You find the port number, and you find some information about the time synchronization. You'll notice the media clock direct equals 0 line. This is interesting. In RTP, the real-time transport protocol, that you have a timestamp, and this should be a timestamp for your media clock. And according to the standard, it should start at a random number. The idea was to make known plain text attacks less possible if you encrypted your RTP traffic. But in most implementations of audio networks, this is 0. The random interval is pretty much always 0. So that's just an interesting thing to note. So you don't need to take account of random intervals in practice. The other information you've got here is basically what type of audio it is. And this is linear PCM 16-bit encoded, 2 channels at 48 kilohertz. If you have done any digital techniques, you probably know what PCM audio is. You basically just measure the amplitude of the signal, and you measure it into a 16-bit value each time, and then you measure it 48,000 times a second. And in this stream, it's a stereo stream, so we have 2 channels of audio. And it also tells us what clock domain we're in, which is quite useful. Okay. So what you can do here is you can just make your own announcement, and then you can make your own name and wait for someone to click on it. That's possibly not so interesting, but it will probably work because there's no verification here, so the client will present all of them equally, and depending on the implementation of your clients, there will be some caching of these messages, and you can probably abuse the caching of these messages to make yourself higher in the list and more likely to be clicked on. So that's one way of doing it, which would work when the stream is set up. But how do we do it when the stream is already running? How can we attack something that's already running? So we've mentioned already that we have latency on our network. So it takes time for a packet containing audio data to get from our stage box to our mixing console. And it takes a different amount of time each time. The variation in this different amount of time is our jitter. So we can't rely on our network delivering something in constant time, which means we have to buffer when we're receiving audio data in our mixing console. We have to buffer it. We have to have a buffer with a fixed offset in time against the clock. We need a fixed offset to ensure it's real-time playback. Otherwise, we'd be speeding up and slowing down each time packets can arrive. And they can also arrive out of order, so we definitely need to buffer it. So what we can do is we can abuse this buffer. And this buffer will be biggest in broadcast applications, because in broadcast applications, you've got higher latencies, because you're typically going longer distances over wider networks. But you can, if you've got sufficient resources, you can probably also do this on a smaller network. You just need to be very precise about your timing. And just to look at what package you're sending here, it's a real-time transport protocol. There's your timestamp, which is based on your media clock. The sequence number, which is there basically to detect packet loss. And in some applications of RTP, you would send basically replies back occasionally telling the sender how much packet loss you've encountered. But in most applications, you don't. So that's not so important to us. And then your payload basically just contains your linear PCM encoded audio. Interesting sort of fun fact here is that you can list your contributing sources. So if you've got multiple audio streams being mixed into one audio stream, you can theoretically keep track of them, but I don't think anybody actually does that. Yes. So how can we abuse this buffer? Well, we can basically play pixel flute, but with a deadline. So you basically just need your packet to be the last packet that arrives, because there's no way to verify the packets coming in, and you're unlikely to spend the time checking if there's anything in your buffer already. Because why would you? And even if you did, then it would just change the game round. So we can basically monitor the network and see when our legitimate source is sending packets. So we sent a packet, and then we can offset our clock so that we always send a packet so that it arrives at the destination just after the legitimate packet arrives, but just before the clock comes along, and then we get played back. And that's basically how you do it. almost got this working. So I hope at some point to have a proof of concept published, because it's not that difficult to achieve, especially on higher latency setups. So let's start to summarize this a bit. Yeah, so we've seen a couple of ways that you can attack network audio. There's definitely more of them. Let's basically just compare. Yes, okay. So why are we in this state is interesting. The AV industry hasn't quite adapted to the fact they're running networks yet. They're running them. They don't understand the implications of them yet. And this is a sort of table that should help us understand the differences and what they're expecting. So as we mentioned, if you've got an analog system, a cable goes from point A to point B. This is, it helps you with traceability. You just follow the cable. It helps you with controlling ingress and egress, because if you unplug the cable, audio stops. It's very detectable, and it creates an actual choke point of a mixing desk where all of the audio is definitely going through the mixing desk, because that's where the cables go. Whereas when you're using audio over IP, the network can basically be routed. The audio can basically be routed in a matrix from any device on the network to any other device on the network. So you've lost that choke point. And the only way to really observe that is to get your net flow data from all of your switches, which is not something that audio engineers are equipped to do or particularly want to do. So we need to find some solutions to that. What can we do in practice today? Well, a lot of these are sort of bad solutions to problems we really shouldn't have. But you can do network monitoring, and if you've got a fixed installation with a lot of resources, then you can probably afford to have a security team look at your network occasionally, collecting data and figuring out what normal looks like. You can disable ports, which kind of works. In practice, it's not going to happen, because someone's going to plug something in last minute, complain that it doesn't work, then just enable all of the ports again, because that's basically the practical side of AV technology at the moment. You could try to implement 802.1x on all of your devices, which has a bunch of management overhead, and your devices probably don't support it. And you could try to do MAC address filtering, but it really wouldn't be that effective. It would increase your attack time by 30 seconds or whatever, however long it takes you to notice that there's MAC address filtering in place and start spoofing your MAC address. Then your other option is basically just segment your network, make sure that your show control isn't running on the same network as your audio, make sure your lighting isn't running on the same network, and just try to minimize your footprint. So how's it moving in the right direction? Well, PTP is getting better. The clock can now be authenticated, which is helpful. And the clocks can also be validated against multiple clock domains. So now a PTP client can listen to multiple PTP clock domains, and then if one of those clock domains is wildly out of sync with the other ones, it can reject it, which is an interesting concept now. So it's kind of a quorum based on what's happening in your network, and there's also the option to do authentication, which I don't think any of the endpoints are really using yet, but it's at least a start. And there's, of course, secure RTP. The only problem with secure RTP is that it's not really got a solution to multicast yet. It kind of goes, oh, you could use it in multicast, but didn't define anything about how you would use it for multicast. So that could be interesting. So what we're missing basically is a usable way to distribute keys to multicast groups. and all of the software and hardware implementations that support it. Because when we can distribute key material, then we've solved a lot of this problem. That's pretty much everything. Yeah, this is my own research, but my employer is also looking to hire a lot of people. So if you're looking for a job in the making loud things, then you can join Holoplot. We've got lots and lots of jobs, really a lot of them. Also, if you just want to move to Berlin, it's quite a nice place to live. Yeah, I think we might have some time for questions.
Thank you very much for the more than interesting talk. Well, if you have questions, please line up at the microphones in the middle of the tent. And while you do that, I have one question. Would be a mitigation to just switch back to XLR?
That is a mitigation, but I think the industry has changed enough that it's not going to happen anymore. I think one of the World Cups, like over a decade ago, was already using audio over IP. So it's definitely in the higher end applications, it's already there, and it's not going back.
So that cat is out of the box.
That cat is out of the box. The only thing we can do now is try to create a secure standard to use and try and get it implemented.
Questions from the audience? You look like knowledgeable people, and it was a highly technical talk. Any questions? No. Seriously? Going once? Yes, please. Come up to the mic.
So, analogous to the XLR situation, how expensive and practical would it be to just apply only physical security to the whole thing?
Well, that's an interesting idea. You could apply only physical security to it, but then you put a switch and a ceiling tile above your bathroom, and I don't know whether you want to put a CCTV camera in your bathroom.
Well, so, I mean, like separating all of these things, because in the XLR situation,
yeah,
everything was physically separated in any way. So isn't that like, well, not a proper solution, but a solution?
Yeah, I mean, physical separation is a good start, and it's going to minimize your attacks, but I think in the size of the venues that exist nowadays, there's always an unprotected network access point somewhere. So you're always going to find something. So there's switches at front of house, there's switches behind stage, there's switches in the foyer, outside. There's lots of different places where, unless you've got security walking around the whole time, or CCTV and everything else, you're going to have a hard time controlling your network perimeter. It's not to say you shouldn't try to control your network perimeter. You definitely should, but the network perimeter, I don't think, is going to keep people out. And maybe also worth mentioning that in a lot of these situations, you've got contract workers coming in with random laptops, introducing random machines to networks. So you could come in already with malware on the laptop that wants to exploit this specific thing.
And probably, if I may add, companies or installations are not keen to implement twice the IP cabling for audio.
Well, that's an interesting point. They actually do tend to build two networks, but not to separate the different things. They tend to build two networks because the way that redundancy is done in these networks is you build two completely independent networks. One's on like 192.168.100/24, and one's on 200/24, and they operate completely separately. And then each device has a primary and a secondary interface on it, and you send the same packet over both. Is basically how redundancy works on these networks. So they tend to build two, but they don't tend to build it for network segmentation. They build it for practical redundancy reasons.
Want to follow up? Please, go ahead.
Yeah, sure. Like, if there's nobody else here. I think the question I was getting at was, did the security actually decrease with the if you would put XLR cables and audio cables through all of your buildings, etc., or you would just put these digital tiny cables in there, did the security actually decrease while moving to digital cables?
I would say that it did, because they generally added more access points to the network. They generally put it in places it wasn't before. So they generally used the versatility that was added, and by using the versatility that was added, increased their exposure. And also, you've then got computers which just come into networks, and you can run a virtual sound card on your laptop and then put audio onto the network. So it's not that difficult to do. And again, these laptops come from, private one-man AV contractor turns up to do a gig, probably uses the laptop for other things, and then God knows what's on there.
Excellent. All questions answered. Anyone else? We still got some time. Think about it. Now's the time. One, going once, going twice. All right. Well, if there are no further questions, I would like to ask you to give another very warm round of applause for this wonderful talk. PC Wiz.
Thank you very much.